So the question now is, suppose a cycle has been detected and it now needs to be recovered. Okay. So how does one recover? That means, so here is the idea. So cycle meaning Ti goes to Tj, Ti is waiting for Tj, this Tj waits for Tk, and this dot dot dot, and finally that is waiting for Ti. Now to break the deadlock, one of them must be aborted, one of these transactions must be aborted. So one of them must be made a victim. So suppose arbitrarily Tk is made the victim, that means Tk is now rolled back. So all the resources that Tk holds is released, which means Tj can now pass, that means Tj will finally finish, and that means Ti can then pass, and so on and so forth. So this is the whole effect of this. So one of them must be chosen as the victim of this. Now the question is, which transaction is the victim? Okay. Now there are many schemes to do that, but there are essentially some heuristics to this. So the first one is the transaction that has the lowest cost is chosen as the victim. Now what does it mean? What does it mean to say the lowest cost? Remember that these transactions are essentially operations, the read write, those kind of operations, and each such read write operation will have some cost. This is by the query processing engine, they will estimate some cost. So the transaction that has the lowest cost, if that is rolled back, that means that the least amount of work is supposed to be redone. So it essentially is it can finish off the most quickly. So if that is redone, that is not a problem. So that is the one with the lowest cost. That is one heuristic. The other heuristic is that the transaction with the least progress. Okay. Now what does that mean? Is that even though we were in the first heuristic, even though the transaction with the lowest cost is being chosen, that may not be a good one, because even suppose it has the lowest cost, but it has almost completed. Now if that is rolled back, then all that work needs to be done. In the second heuristic, what is done is that the transaction with the lowest progress is being chosen. Lowest progress meaning it has gone into its order of operations into the transaction the least amount. So it has essentially done the least amount of work. So it has essentially completed the least amount of work. So if that is being rolled back, or that is being made the victim, then the least amount of work is being lost. So that is the rationale of the second heuristic. And the third heuristic is the one that induces the lowest number of cascading rollbacks. Now this should be very, very intuitive, and this is very, very important to understand that what happens in the case of a database is that if a transaction rolls back, it may have a series of cascading rollbacks. So even though the transaction may have the greatest progress or greatest cost, etc., or if it has been and it has gone too much far, etc., and it has, or the other way around, it has not gone too much far, etc., but if it rolls back, then it will cause a lot of cascading rollbacks. So essentially all those cascading rollbacks, meaning all the transactions that are now rolled back as an effect of this rollback, will need to be redone. So that is a big cost. So essentially the transaction which has minimal effect on the other transactions in terms of cascading rollbacks is chosen. So these are the three heuristics of how to choose the victim or how to choose a transaction to roll back. The next question comes is how far to roll back. So the earlier question was which transaction to roll back, and then the question is how far to roll back. Now of course intuitively one may say that okay, if a transaction is rolling back, it must roll back to the complete beginning of it, to the complete start of this. So that is called a total rollback. So total rollback means the transaction, essentially all the operations done by the transaction are undone and the transaction essentially just restarts. So it is completely aborted. So this is, it's essentially, it's saying that completely aborted, the transaction is completely aborted. What can also be done is something called a partial rollback can be done. Now what is the idea of a partial rollback is that maybe not all the operations in the transaction are wrong, maybe not all the operations in the transaction have caused the problem. So it is rollback, so only that far which there is a problem. The problem is in the sense of, remember that we are not talking in the problem in the sense of recoverability or etc. We are talking in the sense of deadlock. So roll back till deadlock is broken. Now that is the interesting thing to do. Now let us just go back to the example that we did earlier to understand what is being happening. So suppose Ti waits on Tj, that waits on Tk, and that waits on so on and so forth, and this comes back. Now suppose this Ti waits for Tj is being done because of a data item x, alright. Now before that, suppose Tk has held a data item y, and suppose after that it holds the data item z, then it holds the data item w, and so on and so forth. Now the problem is with this x. Now Tk is the victim. Now if x is released, then Tj can succeed, and then once Tj succeeds, Ti succeeds, and the deadlock is broken. So the point is, it will be rolled back only till the point of the problematic data item due to which Tj is rolled, due to which Tj is waiting. So why these operations that involve y, the data item y, need not be rolled back, because y is not causing any problem. So it rolls back only to the point where there is a problem, and then it's released. But this requires a lot of semantic analysis, and the thing is that it has to be known that which is the data item it can hold, which it is waiting for, which is of course known, but it must be also known that this partial rollbacks can be problematic, because even though it can be said that all the operations of y may not be rolled back, but there may be some operations of y that affect the later operations of z and w and so on and so forth. So all of this must be taken care of. In general, by keeping a count of which operation comes after which operation, which the transactions anyway keep at it, then it can be rolled back till the point where the deadlock is broken. Okay, so that's the thing about how far to roll back. Then the question is, the other thing is that starvation in these deadlock recovery schemes, the starvation may happen because the same transaction is repeatedly chosen as the victim. So that is why this starvation may happen. So repeatedly chosen as victim. This may happen because this transaction is doing the least progress, or transaction has the lowest cost, etc. So this is repeatedly chosen as the victim. So starvation, so it may go into this thing. So one interesting way, or one way of breaking this problem of starvation is that when a transaction is chosen as a victim, a count is kept. So a victim count is kept for each transaction, and to break the starvation problem, there may be a threshold number of times when a transaction is a victim. So suppose it's 3. So once a transaction is chosen victim for 3 times, it will not be chosen as a victim for the next time. So it can be starved for 3 times, but not any further. So that is to just to break the thing about starvation. So that is this all the things about this locks and the deadlock recovery, etc. Now there is one thing that is left for the concurrency control protocols, is we have been talking in the concurrency control protocols all along about read and write. Now there are 2 more important operations in databases that are quite frequent actually in transactions that we have not talked about at all. These are insertion and deletion. So what happens when a new tuple is inserted into a table, or when a tuple is deleted from a table, or some attributes are updated, etc. Remember that updates can be handled always as a deletion and then an insertion. So what we will talk about here is the insertion and deletion. So insertion and deletion. So what happens in the case of insertion and deletion? So for a data item x, there are 2 operations that we need to worry about, which is the insert x and delete x. So insert x meaning this x is newly inserted into whatever place it holds to, and delete x is means it's delete. So let us summarize the logical errors. Is that, so the errors that can happen due to insertion and deletion, the logical errors that can happen is that there can be a read of x or write of x before insert x has taken place. So one transaction wants to read an x or write to an x, but it has the other transaction which is supposed to insert it has not yet done. So that's of course an error. Then the read x and write x may be happening after the delete of x. So one transaction which was supposed to read or write this was late, and then another transaction came in. By the time this read and writes came for this transaction, another transaction came and deleted it. So that's also an error. Then there are other kinds of errors which are happening because these are not idempotent operations. So once a data item is deleted, it cannot be deleted again. So the deletion operation is not idempotent. That's error actually. The same for insertion. So once a data item is inserted, another transaction cannot issue another insertion operation because it is already in the place, already in the record or database, etc. So these are the problems with the insertion and deletions. Now note that everything can be very simply handled by assuming that read, insert x and delete x, by assuming that insert x and delete x are similar to write x. So all the conflicts that happens with write is supposed to be happening with insert and delete. That means any insertion, it's a conflict with a write, any insertion is a conflict with another insertion, any insertion is a conflict with a delete. So one thing that I have left out is that delete x is a problem before insert x. So once something is supposed to delete it, but it did it before. So that's a problem as well. So if insertion and deletion are treated like write x, and all the conflicts that write x has is propagated to insertion and deletion, and then the log compatibility matrix and then the conflicts and everything is handled in the same manner as the write x, then everything will be correct. So that is the case with insertion and deletion. So that's the way to handle insertion and deletion. To finally finish the concurrency control protocol, we will talk about one interesting phenomenon which is called a phantom phenomenon. Okay. So a phantom phenomenon is the following, is that suppose there is a transaction T1 that is reading a relation R1 for, let us say, computing an aggregation or something like that, right. So this is a this thing. And then in the meanwhile there is a transaction T2 which comes and updates some field in it. So this is inserted. So this is inserted. So this some field is inserted or some tuple is inserted, and so on and so forth into the thing. Okay. So then T1 and T2, of course, as we can see, this is a conflict. This is of course a conflict because the aggregation will be wrong if it is allowed to insert. But note that strangely enough, this is hard to detect because where is the insertion happening? The insertion is not happening at the relation R1. The insertion is happening inside a tuple or inside a field, or this is a new tuple that is being inserted. So this is a new tuple. So just to highlight, this is a tuple. So this is a new tuple that is being inserted. That tuple of course was not locked by T1, there was no tuple earlier. So when R1 is locked, even in the IS mode and all of these things, everything that is locked below, we cannot lock this F11 because F11 doesn't exist at all. This tuple didn't exist. So this is being inserted. So how to handle this? So this is why it is called a phantom phenomenon, because when R1 is being locked, they do not lock this, but they logically conflict on something called a phantom tuple. So this is logically conflict on a phantom tuple. Why is this phantom? Because R1 doesn't know the existence of it. So for R1, this F11 is a phantom tuple. F11 doesn't even exist for transaction 1. So for R1 for transaction, so this is a phantom tuple. That is why this is one of the hardest problems in databases to catch. So the insertion on a thing is hard actually, this phantom phenomenon. But so this is known as a phantom tuple, this F11, and this whole phenomenon is known as a phantom phenomenon. Alright, so that is the thing of this. So exclusive lock, now how to solve this essentially is that one must get an exclusive lock on this relation R. So this is an exclusive lock that is being brought. So whenever this is being read, etc., this exclusive lock. So the multi-granularity locking actually can solve it. Whenever this thing is trying to insert it, it checks all the way up its parents and see that R1 is locked in a S mode because this is being done. So this cannot be inserted. So insertion is essentially an X lock, but this is already locked in a shared mode, so it cannot get an exclusive lock on it. So the multiple granularity locking actually solves it. So the solution is the multiple granularity locking that we saw earlier, but this is just to highlight that this is one of the very hard problems, interesting problems to catch. So this is a phantom phenomenon. And just one thing to end the concurrency control protocol, we have been talking about the databases, relations, etc., and all of these things, but the databases also use the index structures. So the index locking must also be taken care of. So the varieties of things in the index must be locked. So the index nodes may need to be locked, and the index nodes, locking an index node essentially meaning locking the data items that the index node corresponds to, etc. So this may also help to avoid the phantom phenomenon, because the insertion, etc., is always happening through the index lock and the index through the index node, and the index is already locked because it will touch that particular tube. Okay, so that finishes the module on concurrency control. We will next go over NoSQL and big data.